Been empty for 3 days. Okay, so James Joule discovered that the amount of thermal energy released in a unit of time or power, and he did this by experiment, is proportional to the square of the current. So power is proportional to current squared. There's resistance involved, so I think that would be the formula he kind of came up with. We know from Ohm's law that V is I over R, so if I solve that thing for R and plug it in here, then power is V over I times I squared, and we can simplify that a little bit. Power is a product of voltage and current, and I think that's the only one you're given on your formula sheet. P is IV. But you know, with Ohm's law, you can solve that a couple of different ways. P is Ri squared, or if I just want that in terms of no current, what's I? I is V over R. So that's another formula. P is V squared over R. Okay? So depending on what you're given, I don't know what you want to use to calculate power. Okay? There's 3 options there. Like I said, that's the only one on your formula sheet. But you guys are in Physics 12. You should know how to rearrange that, right? Okay? Your choice. Okay, so remember, power is in what unit? Yeah. But I guess the watt was already taken, so we named something else after James Joule. Watts. And 1 watt is 1 joule per second. So I guess we can put per 1 second. Okay? That's a terrible W. And remember, I am the son of Watt. It's true, right? That's where the word came from. Johnson is the son of John. Fredrickson is the son of Frederick. So on and so on. And after a while, we didn't care. We just, you know. So what do we want to do? Just do some questions on power and then do some notes later? Or you just want me to do series in parallel right after this?
Do it all.
Do it all. A 12.1, what's that thing mean? Ohms, which is a resistance, draws. What's this thing mean? Amps, which is a I, which is a current, which is charge per unit time, coulombs per second, but it's odd to say that, not say current. Not that you're wrong. Into the wall, because that's where we get this stuff to work, right? What must be the resistance of a European 240 watt hairdryer? Did I say watt? Getting old. 240 volts. Hairdryer, if it draws the same amount of power? Question mark. Quite a bit of words. I know the resistance of this hairdryer. I know the current. Could I find the voltage? Sure, V is IR. Do I care? Let's read on. When plug blah blah into the wall. What must be the resistance of this hairdryer if it draws the same amount of power? Well, what is the power of this hairdryer? Do I want to know the voltage? Well, I don't really need to, but hey, that's the only formula I got. Maybe I better find the voltage. I don't know. How else can I make this formula? I squared R. I know the current. I know the resistance. Okay, let's use that one. 9.5 squared times 12.1. 1,092 watts. Does that sound like a lot? I know what 80 watts in the stereo sounds like. It almost hurts your ears. That's average for a hairdryer. They suck a lot of electricity. Okay, that's the power of this hairdryer. What's the resistance of this hairdryer if that's its power? Well, I know power is V times I. And if I know the power and I know the voltage, could I figure out the current? Yeah. Okay. Well, so the current is not the resistance, but I can find the current. It's 1,092 divided by 240, which is what? Do I have that? Is the current of this thing 9.5 amps? Don't, just because it says for that one, don't assume it's this one, okay? It's 4.55 amps. Now, resistance, Ohm's law says that. Okay, that's why I needed I here. I know V, I don't know I. To get R, that's V over I, which is 240 over 4.55, which is 52.7. What's the unit for resistance? Ohms. Okay? Different hairdryer, different current, different voltage. Just because you see a number in there, don't throw it down in this one. So that's enough for current 1. Okay, you should have done 2/3 of it, whatever number it was, I can't remember. Okay, that's enough to finish it. Which? V is IR? Well, Ohm's law. You solve it for it. All right. Series and parallel. Got a little bit. Series. You've been cheating, Don. In a series circuit, only one choice for current to go. Got a 12-volt battery. Is that a series circuit? Any options for where this water in this pipe is going to flow? Nope. No options. You only got one choice. That's what series means. These two resistors are in series. There's no other choices for where the water can go. That's 3 ohms, and that's 5 ohms. Okay? So, if there's only one choice for the current, then the current must be the same everywhere in a series circuit. And I told you yesterday, where would we put this ammeter to measure it? It doesn't matter. Don't write this. I can put it there, I can put it here, I can put it there, there, okay? Doesn't matter. It's going to read the exact same current every time, because that's the only choice we got. Just like water, okay? So, I'll put a question, but I'm not going to answer it for a while. What is the current in the circuit? And again, doesn't matter where. And the voltage over each resistor. So, what's going on with voltage? I know the current, I got that down. The voltage in a series circuit. Do you have any idea if these were 2 light bulbs, which one would glow? The first one, or the second one, or both? They both would. So if the voltage was totally consumed by, first of all, which way does the current go here? Big one's positive. Electron flow is this way. So current flow goes opposite electron flow, because it's backwards and stupid. So you would think that this guy would maybe be brighter than that guy, because that's where the current goes first. But what happens is, for some strange reason, this resistor knows that there's another resistor hooked up. So he's only going to consume a partial amount of the voltage and leave the rest for the other guy. If this was the only bulb here, he would consume all the voltage. Okay? And when it got back to the battery, it would have none left. So the voltage is partially consumed by each resistor. Now, if they were the same resistance, I think we could assume that then the voltages would be equal. But they're not. Okay, so there's a disproportionate amount of voltage in each one. Okay, but the total for a series is a sum of all the voltages consumed in the circuit. Here I only got 2. But if I had 10 of them, then the voltage would be split between all 10 resistors. And then it was 0 when it got back to the battery. You get some more voltage, more potential difference. So all the voltage is consumed always by the time it gets back to the battery. Of course, at some point, there will be no more potential difference in that battery. It'll all be consumed all the electrons will be gone, and then it's dead, and then the bulbs don't glow anymore. Okay, so something else about series. Resistors in series can be added together to get a total resistance. Okay? So R total is R1 plus R2, and if I have 16 resistors all in series, as far as this circuit's concerned, I could just add them all together to get one resistance. Okay? Total. Here I have 12 volts. So V 3 ohm plus V 5 ohm has to equal 12 volts. So if I figure out the voltage on one, I know what the other one is. I can just subtract it from 12. If I have 10 things, they all add up to the total voltage because all the voltage is consumed by the time it gets back to the battery. Okay? So now let's look at this. What's the current in the circuit and the voltage over each resistor? So in this example, it's the same circuit as, that's still 12 volts, but I'm going to add these two. Let's actually do it like this. I'm going to add these two together and go, that's 3 ohms plus 5 ohms. That's the same as an 8 ohm resistor because I can add them together because it's series. And V is IR, total for the circuit. So if I want to know the current here, that's V over R, which is 12 over 8, which is 1.5 amps. That's the current. That's part of the question. Okay? So what else am I asking? What's the voltage lost over this resistor? Well, what is V of 3 ohms? What's the voltage across there? Do I know Ohm's law?
Yep.
V is IR. What's the current through this resistor? It's 1.5 amps because it's the same everywhere, right? Current is the same everywhere. So I know that's 1.5. I know the resistance, that's 3 ohms. So V3 is 4.5 volts. So what's the voltage over the 5 ohm? Well, it gets kind of messy there. Let's put it down here. V over the 5 ohm, well, V is IR. The current is 1.5. The resistance is 5. So that is 7.5 volts. But did I have to do that? Yeah, I didn't. Because I know if 4.5 get consumed by that guy, then the difference must get consumed by the other one. Okay, so subtract 4.5 from 12, you get 7.5. All right, so that's series quickly. That's the easy one. So tell me, if this bulb burns out and it doesn't make a circuit anymore, does this one glow? No. That circuit is now broken, so the current cannot flow. Do you know they used to make Christmas light bulbs for your tree in series? Anyone had the pleasure of trying to figure out which bulb was burnt out because the whole string went dead? Isn't that ridiculous? It would be like in your house. If a light bulb burnt out in the bedroom, everything in the kitchen turned off. How is your house wired? Not in series. Your house is wired in parallel, meaning there's more than one path for the current to go. Okay, so let's do a little parallel circuit. Same battery. There's one path. There's another path. So if there's water flowing, it's got a junction here, right? Some of the water can go that way, some of the water can go that way. There's two paths. These resistors are wired in parallel. That's 3 ohms. That's 2 ohms. And because the current can go in 2 different places, obviously the current must be different, right? If that's a pipe of water and it gets split, we know that I2 must be smaller than the total current we had. And it actually kind of makes sense that I2 plus I3 is equal to the total current because they get split in 2 directions, right? Okay? So current I total is I2. Where'd it happen to I1? I don't know. I just called that 2 and 3 ohms, so I2, I3. But how many different ways it's split? It all adds up to the total current. So what did we know about voltage for series circuits? Once it got back to the battery, it's all consumed. It's all gone. So the voltage that goes this way, same thing. It all gets consumed by the time it gets back. If this electron or series of electrons chose to go that way, it also all gets consumed by the time it gets back. Okay? So what does that mean for this circuit? If I got 12 volts, how much is consumed by this resistor? 12 volts. How much is going to get consumed by this resistor? 12 volts. It all gets consumed by the time it gets back to the battery. It doesn't go this way and then loop around and go that way again. Okay? It just doesn't. It's all consumed by that resistor, all 12 volts. No. Okay, remember our little video, the buckets of charge? That whole bucket goes this way. And that's the only place it's going to dissipate its charge, its energy. Okay, so it's all gone, all 12 volts there. So what can I say about voltage? it's VT equals V1 equals V2 equals V3, okay, for parallel, because it's all consumed, irregardless of what path it goes. You can just treat that as a series circuit, one there and a different one here, as far as voltage goes. So kind of opposite, parallel to series, as far as the currents and the voltages go, right? Okay, what about resistance? In series, all we do is add them up. Here, do I want to generate this formula or just tell you? Okay. That'll save a few minutes. If you want to know why, it's just Ohm's law. Okay? That's how we get the equivalent resistance. The total resistance is 1 over R1 plus 1 over R2, etc., etc. It's a little bit of algebra math, but you remember your little 1 over button on your calculator? It'll come in handy. Okay, so, question. What we want to do when we solve a parallel circuit is we want to make it a series circuit. Okay? So what is the equivalent resistance for this guy? I want this thing to be the same as this. I just want to make that 3 ohm and 2 ohm resistor in parallel, one resistor in series. What's the equivalent resistance? Well, the total resistance of a 1 ohm and a 3 ohm is just doing that. So what's a half? It's a half. Plus a third is that. That's not RT, that's 1 over RT. So how do I get RT? I hit 1 over that. Okay? So that's the same as a 1.2 ohm resistor in series. That might kind of make sense. That's 3 ohms of resistance. The higher the number, the more resistance there is. That's 2 ohms of resistance. More is going to want to flow this way than that way. But if I got 2 choices here, whenever you have 2 resistors in parallel, it always better be a smaller number, right? Because there's 2 paths here. That's less resistance. So that's the same as 1.2 ohms in series. That doesn't make sense, don't worry about it. Okay, what is... Now I have to be specific here because it's not just what's the current, because there's 3 different currents here. What's the current at the battery? V is IR. At the battery, I know V is 12 volts, right? But now, since I can treat this as a series circuit, that's the equivalent resistance, and the current here is the same everywhere, so that's why I want to do that. So I can figure out the current at the battery. 12 over 1.2, that's a nice 10 amps. What else do I want to know? Current at each resistor. Resistor. Okay, so the 3 ohm resistor, what's I3? Ohm's law. V is IR, so I is V over R. I know the resistance of the 3 ohm resistor is obviously 3. What's the voltage across this guy? 12 volts, because they're all the same, okay? All of it's lost when it goes across there. So that is 4 amps. Now, think common sense. If that's 10 and that's 4, then this must be what's 10 minus 4? Yeah, okay. That's a good guess, but let's prove it. What is I2? 12 over 2, 6 amps. Okay. Now, does that make sense? More current goes through that one than this one. Does it make sense? Yes, because it's a smaller resistance. Less resistance, more current. Okay, that's it for starters. Oh, we got lots of sheets.